Okay, so this week we're going to get into quadraphonic sound. And in preparation for that, the first thing I've done is configure the studio for this first quad setting, quad XY, where we're imagining the studio space as looking sort of top down, with 4 speakers, 1 in each corner of the room, reading the speakers left to right, front to back. And so for that, I've connected the first 4 outputs of the Mo2 to front left, front right, back left, back right. And keeping in mind that in Supercollider, this red cable corresponds to output 2, and then orange is 3, yellow 4, green 5. So anything we send out to on audio bus 2 comes out front left, anything on 3, front right, etc. So that's how the mixer and interface are currently connected. So we'll open up Supercollider, and we'll start by configuring our server. If we were doing stereo, then we could get away with just 4 output bus channels because we need to skip over the first 2 on the Mo2 because of the way that's connected. But for quadraphonic, we need at least 6. We could actually stop there. We could do 10. There's no harm in doing more than we need, but we'll keep it at 6. And we also want to record that many channels. And then boot the server. And that is what we want to see in the post window, Mo2. And now I've pre-copied some code that will read some sound files into an array of buffers. And it doesn't work yet because we need to actually save this file so that this process, now executing path, will actually return something meaningful. So I'm going to save this as code and put it in Field Steel Week 5 right next to my sounds folder. And so now this buffer reading code should work. That is what we want to see. And so what I have today, and again, I just have probably over-prepared. I'm not sure we're going to use all of these sounds, but I have some flute sounds. I have these 3 multiphonics, these 5 tongue rams, and then these 3 whistle tones. And so let's actually go ahead and play these. Let's see, so we say B at 0. Oh, no, what am I doing? Yeah, okay, play buff. I think, well, okay. What I, normally what we see when we read these is we just read onto the server and a string representing the full path. So if we do that, B at 0 dot num channels, these are stereo sound files. So 2 channel sound files. So we'll go ahead and just read that anyway. Done action 2. And before we play this, we'll open up the meters and also bring up the node tree. That's a nice thing to have handy just so we can make sure we have some idea of what's living on the server at any given point in time. So let's play this and see if it works. Yeah, so that's our multiphonic, and it is a stereo file. And then 1 and 2 sound very similar. They're just slightly different samples of the same thing. The tongue rams sound like this. And then the whistle tones this kind of thing. So yeah, 11 samples in total. Because we're going to be doing quadraphonic work, it makes sense to me to work with monophonic files because that's sort of the smallest, simplest, individual unit sort of thing that we can deal with. We can, of course, map stereo files into quadraphonic space if we wanted to, but to keep things simple, we're going to do monophonic files. And the way I'm going to do that is simply just read only 1 channel of these files. So as we read these 11 sound files into buffers, we're going to use the method read channel instead of read. And this method gives us a slightly different set of arguments, and one of them is channels. And we provide an array corresponding to the channels we want to read. So if we provide the array 0, just square brackets and a 0, we're only going to read the 0th index channel on each of these. So basically just the left channel on each of these. If we specified 1, then we'd read the right channel on all of them. But just arbitrarily, I'm going to go with the left channel. So now we run that. Technically, it's probably a good idea to buffer.freeAll. There's really no harm in not doing this, but just for clean think, we should release all the buffers we've previously loaded and then load the buffers. Right? So now b at 0 num channels is 1. Right? So all these sound files are now monophonic, and that's good. So now if we play this again out to 2, we just change this to 1. Right? And now we have confirmed that these are all one-channel buffers. So great, our sounds are loaded, and we're ready to make sounds. So we're going to start by making a simple synth def. And I want us to get in the habit of making synth defs. It's just a more robust and flexible method for creating sound. It just gives us a lot more possibilities. It's a little bit cleaner and tighter than just doing a function.play, which is less reusable. So we'll start with a variable, like we always do, declare a sig. And just, I get this question from time to time. I just use sig out of habit. It can be any word you like. I just like sig because it's short and it's meaningful. We'll make this a play buff. It's going to be a one-channel buffer. We'll make an argument so that we can specify an arbitrary sound file for this play buff to play. We'll do a rate argument. That's a nice thing to do, and we'll just do done action too. Okay, so we're going to need that argument for rate, initialized to 1, and we will go out, an argument for out, and our signal. And in our synth-def, we'll initialize our out to 2, because that's how Studio X works. That's how we've got the Mode 2 configured. And then we can just simply add that synth-def, close our parentheses, and that's good, no errors. And now let's confirm that it works. This should make sound, right? And it just defaults to the 0th buffer that we loaded, or the buffer with buffnum 0. So just to check that we can actually specify other sound files. That's good. That's all working. And now, because we've specified an argument for the output bus, we can say 3. And let's go back to our tongue rams. So there's front left, front right, rear left, and rear right. That's going to sound, hopefully you'll get something resembling a surround sound experience with this stereo room recording. But if you copy what I'm doing in Studio X, you will get a lovely, true quadraphonic experience. Just something fun we can do right off the bat is just randomly choose an integer between 2 and 5. If we clear the post window and just run this segment a little bit, you can see that we're getting integers between 2 and 5. So now every time we run this code, we get a sort of discretely placed sound in one of the 4 corners of the room. And with our current design of our synth-def, that's all we can do. We can't, position a phantom image of a sound somewhere in the space between 2 speakers, or to our left, but sort of to the front, and to our rear, sort of to the back. So we have to modify this a little bit in order to do that. Before we do that, let's just make sure rate is working. Maybe we can do X brand between 0.5 and 2, so a full octave in either direction. That's fun. If you like to think in terms of semitones, MIDI notes, etc., you can do a linear distribution somewhere between some number of half steps. Let's just go 1 half step down and 1 half step up. Now, because these are integers, this is going to give us 0, 1, or -1. But that's not good for a raw rate value. We need to say .MIDI ratio. And this converts that into the correct ratio to transpose up by a half step, down by a half step, or leave it alone. So we'll just get 1, 1.0594, or 0.9438, blah, 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 blah. So this gives us if you wanted to do a full octave, you could do like this. And with RRAND, if you specify an integer for the min and max, then you will get integers back from RRAND. But if either or both of these are floating point numbers with a 0.0 or point something, a decimal in them, then you'll get floating point values. So this gives us, we're no longer locked to the chromatic scale here. So it just sort of gets out of tune, you might say. Okay, so that's, we've just barely scratched the surface of dealing with quadraphonic sound. This is a very simple way of just positioning a sound in one of the 4 speakers. But we can do better than that. We can actually use a quadraphonic panning unit generator. Pan4. And we'll take a look at the help file for this. We're going to cursor over to Pan4 and take a look. So Pan4 is a 4-channel equal power pan. It takes an input signal and it takes an X position and a Y position. So the best way to conceptualize this is think of the room as a Cartesian coordinate system. If you were sort of looking down, right, just from the top, and -1 for X position is hard left, +1 is hard right, just like Pan2, but then we also have a Y position. So -1 is in the rear of the space and +1 is in the front. So we will provide, let's say, so we need to put our signal in there, and then we'll just say X and Y, and we are going to declare, let's see, yeah, let's declare some arguments. We'll initialize these both to 0. And I just want to point out, this is a subtle concept, but we do have the option of using single character lowercase letters as global variables. Right? These will persist through multiple evaluations, and they're accessible in sort of everywhere. But these are different if you declare a variable with the same single character lowercase name in a function as an argument or a variable. It has local scope, and it's different. It's independent and different from this one. So there's nothing wrong with doing this. It's absolutely fine. But if you want to use longer names, that's fine as well. So we'll just rerun this, re-add this synth-def, and I'm gonna space out our synth a little bit, just so we can maybe see these argument values a little bit clearly, a little bit more clearly. And so I think that's fine. And we'll parenthesize this and comma, and we'll say X is -1 and Y is +1. So this is hard left and all the way to the front. So it should come out of just output 2. No, output 4. I guess, what am I doing wrong here? Right. What did I do? Why? I'm not sure what I did. Okay. Oh! Okay. I did something very silly. I'm still picking a random value for the output bus between 2 and 5. Yeah, and so Pan4 takes a monophonic signal and turns it into a 4-channel signal. And if we output on bus 2, then the remaining channels will be on 3, 4, and 5. If I output on bus 5, the remaining channels will be on 6, 7, and 8. But those don't actually exist. We didn't even allocate those as hardware buses. So when you are using a quadraphonic or octaphonic or anything panner, you always want to be outputting to the lowest numbered hardware bus. You don't want to be goofing around with that. And so now, if we pan hard left and all the way to the front, then this puts the signal exclusively in the front left, which is bus 2. Yes. That's what I expected. So if x is +1 and we leave y alone, that's the front right. And if we set x to 0, we get equal signal in 2 and 3. So we're creating a phantom image in between the front speakers. So it's a centrally placed sound. And if we move to the back, now the sound is centrally located behind me. Here's the rear left corner and the rear right corner. So now we can do something like rrand -1.0, +1.0, and just copy this in below. And so now every sound will have a random Cartesian point in the space. Right. Certainly a more exhilarating experience if you're actually in the quadraphonic space rather than listening to a stereo version of it. But so take my word for it. This is definitely a full, rich, random quadraphonic experience. So let's switch over to I mean, just arbitrarily just changing the buffer here could make for an interesting experience. Just now we're listening to the multiphonics instead. And I think I will narrow the range of pitches that we can choose from here. We'll just go between -7 and -6.5 and just run a few of these. So these all have slightly different playback rates, and each one has a random position somewhere in this 2 space that we're working in. So anyway, it's kind of a nice immersive sort of thing. But let's instead of initializing our synths with fixed points, let's make it so that think about how we would actually get a sustained sound like this multiphonic to actually move around the space. You know, actually sort of seem like it's a point source which is moving around us. So what we can do here is delete these and make variables instead. And these variables x and y are going to hold UGens. Are going to keep a reference to various UGens. So we'll do LF noise 1, and we'll do the same. We'll do another one for y. And LF noise 1 generates random values at a frequency. We'll make it fairly slow to begin with. Both of these just picking a new value every 5 seconds. And by default, the output range of LF noise 1 is -1 to +1, which is perfect for this particular application. So both the x-coordinate and y-coordinate of Pan4 will be linearly moving randomly through the space with picking a new value and moving towards it linearly every 5 seconds. So now we don't need to specify these x and y values anymore. They're x and y are autonomous UGens. They're moving values. So we'll just play one of these and watch the level meters. Yeah, that wasn't very exciting. It's a very slow moving noise generator, so we might speed that up a little bit. Yeah, okay. We can make a few of these. And we can sort of compare this and contextualize this in comparison with what we just did, where we specified a fixed x and y point for each sound. And in doing that, we position sounds, multiple sounds that are all slightly different with different playback rates, just barely, at different points. But then those sound sources that we place in the quadraphonic field, they don't actually move as they sound. But now that we've used unit generators to control the x and y position, each of these sounds that we create sort of meanders around the space, sort of moves around us, moves in front of us, moves behind us, moves left to right. And then if we run this multiple times, then we have multiple sources which are moving independently and uniquely. So it becomes a much richer experience. Yeah. So let's see what's next. If we wanted to, here's something which is sort of interesting. Let's imagine how we would get a sound to move in a circle around us using Pan4. We would need to we'd need to harken back to our days as trigonometry students, and remember that we can think about sinusoidal motion as movement around the unit circle, with the x coordinate being controlled by x and y coordinates of circular movement generated by a sine and cosine. So all we need to do is just use two sine wave generators, one for x, one for y, and sort of have them do the same frequency, run at the same frequency, but have them be slightly out of phase. So for instance, let's say we want to start with the sound directly to my left. So panned hard left for the x position, but the y position should start at 0. So we're going to make this is a sineosc.kr. We'll do a slow frequency, 0.5. And the initial phase of the x position, because it's hard left, so that's an x coordinate of -1. And where's my sketchbook? Let's get my sketchbook real quick. Open this up. And so a sine wave, right, it has this default phase. Phase 0 starts here. It goes to +1, back to 0. And then at 3 pi over 2 radians, it's at -1. So we want our x position sine wave to start right here. So we will say 3 pi over 2 for phase. And for the y position, we want that to start left. And then we have to say, do we want this to go clockwise or counterclockwise? So if we want it to start on my left and go to the front of the room, it's got to go from a value of 0 to +1. So actually that just needs to start with an initial phase of 0, because it'll start at 0 with an initial phase of 0, and then go up to 1, the front of the room, back to the sort of the middle, the sort of the belt of the room, and then down to the back of the room, and etc. So this one will have an initial phase of 0. Oops, and we didn't change this to sineosc. We need a sine wave. That's what we need. Okay, so now I believe this should move in a circle starting on my left. So that would start with speakers 2 and 4, and then we'll see it move to just 2 and 3, and then 3 and 5, and then 5 and 4 as it's in the back. So I might need to slow these down so we can really see it, but I hope this will work. I think it will. Yeah, that is quite fast. You can't really see what I described. So if we make these very slow, yeah, 5 and 3 and 5 and 4. Yeah, so that's our circle. So we can sort of send one around the circle, and then another, and then another, and then another. It's like we're It's like we're in a cemetery and we have like a choir of ghosts like circling around us and moaning or something. I don't know. Yeah. So that's Pan4. Lots of flexible options there for you to sort of explore. If we wanted to even develop this even further, we maybe would even want to say let's specify a frequency for these x and y sine waves, so that we can make them maybe go at different speeds, because that would be very interesting. When these are both running at the same frequency, we get a circle, and we'll initialize these to, I don't know, to 0.5 or whatever. Y freak is 0.5, but if we made let's see, this is where I really have to think hard about this, but if we made one of these twice as fast as the other, instead of let's do a top-down thing. So here's our room. Speaker, 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 right? Going in here, making sound waves. So with both of those running at the same, with the phase offset in the same frequency, it does a circular path like this. So it makes one full cycle horizontally and one full cycle vertically. But if one of those sine waves is twice as fast, we'll either get something. Let me undo these so we can see this clearly. We'll get a sort of figure 8 type thing, like this. So that would be if the x position has twice the frequency. You see, it makes 1, 2 full cycles in the x position, but the y, the vertical, just makes one full cycle in that same time. And if we switch those, it would be a figure 8 the other way. And if we did like a 2-to-3 ratio, now this I don't think I'm going to be able to draw this. Yeah, I'm going to goof it up, I'm sure. But it's these are if you do an image search for Lissajous curves, then this is sort of what we're talking about here. Lissajous. Anyway, it makes for some very interesting harmonic patterns in the space. So let's go ahead and try one of those. We will say let's make this 0.5. So we'll make it an octave lower, so it's twice as long. That'll give us plenty of time to sort of savor what's happening with our sound. And we'll say x freak 0.2, and y. No, we'll do 0.3. And y freak 0.15. So this should be a sort of figure 8, I think. Yeah. I'm sitting here in Studio X. I think that works. And let's do a 3-to-2 ratio. Yeah, hard to visualize the patterns even listening to it, but we can then go take it even further and just say, you know what, just randomize that. Just make each one random, and then we'll make a bunch of them. We can even randomize the playback rate just a little bit. Okay, so I think that probably makes the point clear about what Pan4 is capable of. It's really good, especially when you're thinking in terms of Cartesian systems, but it's not the only option for quadraphonic panning. There's another panner which I would like to devote some attention to, and it's different enough that I'm going to make I'm just going to copy and paste this synthdef and I mean, I guess I might as well just give it a different name, play 2. Yeah, play 2 is fine. And we're going to trash these arguments, trash these variables, and we're going to say, get rid of those. We play our monophonic buffer, and then we're going to say pan a z, capital A, lowercase z. And let's go ahead and help file this. Command D. Pan AZ is, AZ stands for azimuth. And the way pan AZ works is it assumes, it assumes you're working with an equidistantly spaced ring of speakers. It can be any number of speakers. And right now we're dealing with 4. And that's the first argument we give to pan AZ, is the number of channels. So that would be 4. And the next argument is the input signal to pan. And then a position. I'll just read this in case it's too small. Pan position, channels are evenly spaced over a cyclic period of 2.0 in pause with 0 equal to channel 0 and 2 divided by number of channels equal to channel 1. Okay, this is a confusing description. This paragraph is sort of clears it up. All channels will be cyclically panned through if a bipolar sawtooth wave from -1 to +1 is used to modulate the pause. So we'll go ahead and do that for now. We'll say LF saw, low frequency saw. This is different from regular saw, which is an anti-aliasing saw, which actually has a fairly wiggly shape. LF saw is just a nice clean diagonal ramp. We'll control rate that. And we will say, you know what, why don't we actually get fancy here, and we'll say buff_dur.ir of buff. So whatever buff we pick, it's going to, and we need to do the reciprocal of this. It's going to take the duration of that buffer, you know, whatever, however long it happens to be, it's going to be the duration, and then we take the inverse of that to give us the frequency that we would need for LF saw to go through one cycle of its waveform. And there are some other arguments after pause. We need to close out LF saw, right? And so next is level. This is just simply an amplitude control. We might as well throw one in there. You know, we didn't have one earlier, but it's nice to be able to adjust the amplitude of a sound. And then width. Width is basically how wide the panning is at a particular point around the circle. So 2 is the default, which means it pans between 2 speakers, has a width of 2 speakers. You can make that narrower, but you'll get sort of silent gaps between speakers. And you can also make it wider, so it pans between like 2.5 speakers or 3 speakers. I usually just leave it at 2. You can mess with that if you want. And then orientation. This is important. Should be 0 if the front is a vertex of the spanning polygon. In other words, if there is a front speaker in your setup, in that case, you specify 0 for orientation, and the lowest numbered hardware output bus goes to that channel, goes to the front. But in our case, right now, we're working with the 4 speakers in the corner, and so in that case, 0.5 is the correct orientation. So it treats the front left speaker as the lowest hardware output, and so this just sort of, well, the right word is orient. It just orients the azimuth panner correctly, so it's not, you know, slightly askew. This should give us a circular sweep, so that the sound starts at -1, which is the back of the space, and it moves around to 0, or sort of in a clockwise fashion. So 0 is the front, and it'll continue to a value of 1, which again is the back of the space. So we will say synth.new play 2, play 2, thank you. Buff, we'll say be at 0, out 2, and that's fine. we can stop there. So I guess we can sort of watch the level meters. Let's get a sense of how long this will take too. Be at 0 dot duration. It's 5.11 seconds. So okay, that sort of worked. It started in the front, and that's because the LF saw does take a phase argument, which is by default 0. So a LF saw looks like this. That's really bad. Okay, let's try again. Come on, just a vertical line, please. All right. Right. So +1, -1. So this is if you specify a default phase of 0, it starts here, and 0 for PanAz corresponds to the front of the space. We want to start it here, right, at this value, right, -1. So we just need to specify a pan position a phase of whatever puts us halfway through here. And I always have to look up the help file here. So yeah, the phase, for efficiency reasons, the phase of LF saw is a value ranging from 0 to 2. So 0, 1, 2. So we just need to specify a phase value of 1, and that will cause it to start at this discontinuity here. And +1 and -1 both correspond to the rear of the space. So yeah, we just specify 1. And now it should start in the back. So it should start at 4 and 5 and then rotate around to the front. And it's not quite working also because I've forgotten a very important thing, and that is when we are working with PanAz, or quad circular panning, and we're using the corner speakers, we need to repatch the mixer, because PanAz sees front left as the lowest hardware output bus, that's 2, and then it goes around in a circle clockwise. So that's front right, and then we need to set the third output to back right, and then the last one to back left. So for working with PanAz in corner of the room quad, we need to swap these two. So I'm going to stand up and do that right now. Okay, so that won't look any different on Supercollider, and it might not sound all that different because of the stereo room recording. But for me, I think this is going to be correct. So it should start in the back, move around my left to the front, and then around my right to the back. Yeah, much more convincing. That's absolutely correct. So just make sure you've got to repatch the mixer, depending on what kind of panning situation you're doing. You know, what kind of how you're conceiving of the space. Whether you're thinking of it in a circular way, sort of with polar thinking, like or Cartesian, sort of XY system. Yeah. So let's. We could even now go back. Let's just, instead of this, we will just do a straight pause pan position, and we will default that to 0, which is front center, and run that again. And now if we randomize pan position, that we want to give it a value between -1.0 and +1.0. Because we do want floating point numbers, we want to do the full circular space and all the floating point numbers in between. So this should, let's go back to some of our tongue ram samples. So this is similar to what we did previously with Pan4, but we are dealing with sort of points on a circle surrounding us. So we could narrow it down to be only between the left side of the space, -0.5, and the front of the space, so only in the sort of front left quadrant. I think that's, yeah. So we'll see absolutely nothing in 4, which is the rear right speaker, but we'll see a lot of activity in 2, and then some activity in 3 and 5. 3 if it's sort of somewhere in the front of the space, and 5 if it's towards the left of the space. Yeah. Maybe we can vary the amplitude as well to keep things interesting. Make things a little bit more varied. And if we want to, we can say 3 through 7, right? So this syntax gives us the array. It's sort of the subset of the items in the array B with indices 3, 4, 5, 6, and 7. So these are just our tongue ram samples, and we can choose one of those. So if we run this segment a few times, we can see we're just choosing buffers with indices, with buff num 3, 4, 5, 6, or 7. And, you know, let's go ahead and space this out a little bit. Just a little bit easier to read. And then for fun, you know, we'll give ourselves rate, and we'll say scale dot minor pentatonic. I'm a sucker for minor pentatonic. Degrees dot choose dot MIDI ratio, right? Okay, so here's our scale, the type of scale, and we're giving it into scale degrees. We pick one, and we convert to MIDI ratio, so suitable for rate. And now that it's a ratio, I'm just going to divide by 2 to go down an octave. And I'd like to use the whole space again. So we're going to go minus 1.0 to positive 1.0. Yeah, okay. And now you can tell by my frantic keyboard mashing that there's a real advantage to using patterns, which we did last week, which is, you know, you can automate the process of generating synths instead of having to sort of awkwardly do it by hand. Although there is an alternative to patterns, it's just a little bit, it's not quite as flexible, but I do find myself sometimes using it, and that is to make a routine, a new routine. The routine is basically a special, I mean, you can think of it as a special type of function, which allows wait times. It just allows you to say to Supercollider, okay, wait for this many seconds, and then keep going. So if we do, you know, this, and then we'll say 0.5 dot wait. You can do it 0.5 dot wait, or you can say wait, and then in parentheses 0.5. You know, same sort of thing. And then we'll just do that a couple more times, and we will play this routine. Yeah, so just a single keystroke, and we get 3 of those. But we don't want to be copying and pasting like that. Better is to do a sort of function inside of the routine. Oops, that's not what I wanted to do. And this internal function, we're going to say dot loop. And whenever you do a dot loop, never run that code before making sure you have put at least one substantial wait time in there, right? If you forget your wait time and you loop it and play a routine, I hope you saved your work, because it's gone. I mean, maybe it'll auto recover. I don't know. I think that's a relatively new feature. But just make sure you put a wait time in here. So. And we can do the array. Let's see, 0.3. Let's do 0.5, and then whatever 0.5 is times 2/3. What is this? Okay, yeah, 1/3. We'll have the array 1/2, 1/3 dot choose dot wait. So we're going to pick one of those and then wait. So. Yeah, so you can see it's not quite as attractive as patterns, where we can use these p objects, p-seek, p-rand, p-white, etc., to sort of describe on a higher level exactly what we want. Like if we wanted to do a complex rhythm here, well, we'd have to, we basically would have to use patterns in order to specify something complicated. It's easy to just pick a random thing, but and then all sorts of other things you can do here. You can divide by 2 or 1 dot choose. So now I'm just putting some space in here for legibility. We might go down an octave, and we might not. And probably the smart thing to do is give this routine a name. We'll call it just tilde r, because once it's playing, you can say tilde r dot stop. And there goes that. And that has the advantage of it will not cut off a synth like command period does. If we have a synth running and it's a sustained thing, we hit command period, we hack it off in the middle. But now we're actually stopping a routine that generates synths. So once one of these synths is generated, then done action 2 will just make sure the synth disappears at the end. But by stopping the routine, we halt the production, the means of production of the synth. So anyway, not that easy to demonstrate with these really short samples. But anyway, that is that's PanAz. Works with quadraphonic, also works with octaphonic, and we'll probably be using this as we go down the line a little bit. So I think that's more or less all I wanted to cover for this week of quadraphonic work. And next week we'll keep doing some quadraphonic stuff, answer some questions, and apply what we know about patterns to quadraphonic space.